Okay, continuing on with confidence intervals. I want us to look at some properties of confidence intervals. And first, I want us to think of this idea of this quantity that I have talked about before in an example called the margin of error. Okay, it's defined to be, now for this confidence interval that really the only one we've developed so far, the margin of error is just the stuff you add and subtract to x bar to get the lower and upper bound. And so you'll notice it's also half the equal to the half length of the confidence interval. The margin of error also gives the maximum difference one can have between the point estimate and the parameter of interest, assuming that the confidence interval caught the parameter. So take a look at this picture. When we think of a confidence interval in its picture, here the midpoint of the interval is x bar. This is the upper bound, x bar plus the margin of error, x bar minus the margin of error. Okay, and so if we think of the margin of error, anything that falls inside this interval, for example, if I'm interested here in mu, I'm trying to estimate mu, it's unknown, but if mu falls inside of this interval here, then the distance between x bar and mu is at most e, or it is at most the margin of error. Okay, so this is a way to think of the margin of error. Now, mu does not always fall in the interval, but assuming the interval is correct, then E is the maximum distance x bar is from the population mean mu. It turns out that this phrase margin of error is used quite a bit, even in on television shows or political polls, this sort of thing, where they are displaying some feature about a poll. They'll give a point estimate plus a margin of error. Okay. All right, so moving along here, in light of the margin of error, we can think of some properties of confidence intervals. The first one here is that the point estimate is in the middle of the interval. All right, and that's what we have right here. Okay. Next is that the standard deviation, if that increases, then the confidence interval, let's think about this. If I increase this quantity here, then what happens? Well, that numerator gets bigger and that whole fraction gets bigger, and then the margin of error in turn gets bigger. So if sigma increases, then the confidence interval gets, we'll say, wider. Okay, and that seems to be intuitive. If there's more dispersion in the population, then your confidence interval is going to have some more uncertainty in it, and that will be reflected by a larger interval. If the sample size increases, so if this increases here, n increases, well, that denominator gets bigger, so the overall fraction here gets smaller, so the margin of error actually gets smaller. So the confidence interval gets, or becomes, the confidence interval becomes more narrow. Okay. Lastly here, if the confidence level increases, now if the confidence level increases, that is, I'm saying this, then 1 minus alpha, that increases. If that increases, then alpha is decreasing, right? And if alpha is decreasing, what happens to z sub alpha over 2? Okay, z sub alpha over 2. If that subscript gets smaller, that forces me to go further out in the tail of the standard normal distribution. So that z percentile actually gets bigger. And so if this z percentile gets bigger here, then the margin of error is going to get bigger, and my confidence interval is going to get wider. So overall, if the confidence level increases, then kind of have my justification here. Then the confidence interval, I'll say the CI, gets wider. Okay. All right, so some properties of intervals. There's trade-offs between the sample size and the width of the interval, and also there's trade-offs between the confidence level and the width of the interval. So be aware of those. Okay, another idea within statistics is through what's called sample size determination. And the idea here is, suppose we want to take a sample. We haven't taken a sample yet, but we want one. And we want our sample to yield a confidence interval of a predetermined width. Or in other words, equivalently of a predetermined margin of error. So with that in mind, how large should our sample size be? Okay, so an example of this might be in the previous confidence interval problem that we had, we were interested in estimating the average age of a civilian worker. Suppose we wanted our interval to have a width of 2 years. We wanted it to be that tight, and so that would mean the margin of error is 1 year. If we force that constraint on it, and we had a 95% confidence level, say, the sample size determination allows me to figure out how large my sample size needs to be in order to have a width that narrow and also to maintain that confidence level. So, so what we want here is we're asking this question. We're really asking this question for a given alpha, which is determined by the confidence level, standard deviation of the population, and margin of error. How large should N be? Okay. Well, let's think through here. What do we know about the relationship between alpha, sigma, E, and N? Well, we know this. The margin of error is the Z percentile times sigma over root N. Okay? So I'm asking the question, I know alpha, sigma, and E, but I want to solve for N. So I'm going to just use a little algebra here. So solving for N, we would square both sides because here I have the square root of N. I want to get to N there. So if I square both sides, then I'll have this expression, E squared equals Z squared times sigma squared over N. Okay, and if you want to get N by itself, you multiply both sides of this equation by N. So you have NE squared equals Z squared times sigma squared. And then going one step further, solving for N by itself, you divide both sides by E squared. And you get this expression here. So what this gives, sometimes you may see it, I think the book presents it this way. It looks at this ratio here and then it squares everything. Omit that 6. But that is the sample size required to have a confidence interval of a margin of error E and a prescribed confidence level and also a known standard deviation. Okay? Alright, so let's look at an example that illustrates this idea, this sample size determination idea. Okay, so of interest here is the mean monthly income of SFA students. Okay, so this is the parameter. We want to estimate mu. It's a mean here. It's unknown. Now we have yet to take a sample to estimate mu. But suppose we want a 99% confidence interval and we want our width to be 300. So that forces our margin of error to be 150. All right, half the width there. So with that in mind, how large should our sample size be? And we're going to assume that the standard deviation of the population is 400. Okay, so using the formula that we developed on the previous page, we have n equals z sub alpha over 2 times sigma over e squared, the sample size determination formula. So let's think about, what do we need? Alpha is 0.01. Okay, so alpha is 0.01 because our confidence level is 99%. So that forces the z value to that's going to go in this formula to be, well, z sub 0.01 over 2, or z sub 0.005. And if you look on table N, you're going to look for the upper this upper percentile. This is the upper 99.5th percentile. Let's see here. Let me try to get back to my screen. There we go. If you look up for that upper 99.5th percentile, you will get 2.575 or something really close to that. Okay, so plugging in here, I'm going to have 2.575 as my z value. Sigma is 400 and E is 150, right? That's the margin of error. If I square that, you do the arithmetic here, you should get 46.94. In terms of sample size determination, the rule of thumb is to always round up. That will actually give you a confidence interval that's slightly more narrow than the requested width of 300. So we're going to round up. So rounding up, our n, our sample size, would be 47. Okay. So sample size determination. This is actually a pretty common place to be within statistics. All right. I want to kind of wrap up this sort of section. We've been under the heading of a confidence interval for mu when sigma is known. And here I'm asking a very important question. If we are trying to estimate mu, then why is the interval formula, and we use this in an example, we also used it as our basis for sample size determination, but why is that formula not practical? Okay, well, you may have picked up on this, but when you look at the items in this formula, what do we need? We need x bar, which we get from the sample. We need z, which we get from the confidence level. We need n, which is our sample size. We get that from the sample. And sigma. Well, sigma is the standard deviation of the population, not of the sample, but of the population. And we're not going to know the standard deviation of the population, in particular if we don't know the mean of the population, mu. And we don't know mu because we're trying to estimate it. That's the whole problem set up here. And it's also, just recall that parameters are rarely known. So this interval estimate is really impractical to use because we don't know the population standard deviation. that is the quantity sigma here. Okay. Because of that, we this formula by itself is not practical. Now it does have its purpose in that it is a starting point to build a practical interval, but by itself, really to write sigma out here and to assume that we know sigma, that's not practical. Okay. All right, so what that does for us is that moves us to the more practical setting of a confidence interval for mu when sigma is unknown. Okay, so we're going to pick up here next.